So in this video, I want to just summarize the previous example that we took a look at. And again, that previous example is the probably most important example to think about in these notes. And so this slide of summarizing that is really the key takeaway for this section. We already talked about how we could find general solutions, and we didn't need eigenvectors for that. And now we can think about, well, what do the eigenvalues tell me about the dynamics of the system? In particular, what do they tell me about solutions that start off near the origin? So when we're thinking about eigenvalues for these systems, they might be real and they might be complex. So let's first think about the situation. If the eigenvalues are real, then one possibility is that both of the eigenvalues are positive. And when that happens, that's when the equilibrium at the origin is very unstable. Okay, and in fact, we would say that this is an unstable source. Okay, meaning what is it going to look like? It's going to have things that are moving out from it. So everything is flowing out from it, and so we would call that a source. If both of them are negative, then it's the opposite. In this case, the origin would be stable, and we would call that a sink. And that's because in this case, everything would be flowing in towards that origin. And some of the cases that we've been looking at, what we saw is that if one of them is negative and one is positive, then we get a saddle point. So we would say that the origin is semi-stable. Saddle point. So there might be some directions that head out, and there's going to be some that go straight in. And this holds whether we have two distinct or one repeated one. So if I have a repeated root and it's positive, then it's going to be an unstable source. And if I have a repeated real root, which is negative, then the origin is going to be a stable sink. So the only way we get a stable equilibrium when we have real eigenvalues is if both of them are negative. Okay, in the case where we had purely imaginary eigenvalues, then this was the situation where the origin is a center point. For elliptical orbits. Okay, and this we would consider it stable because solutions that start near the origin are going to stay near it. Okay, we don't head back in towards the origin, but we also don't head far away from it. So we can consider this as some sort of stable point. And so that would mean that the origin is in the middle of some ellipse, and then we have some ellipses that are orbiting around that origin. And for the last case is what happens if we have complex eigenvalues where the real part is not zero. Well, then the stability is going to depend on the sign of the real part. So if alpha is negative, then the origin is stable. And we're going to call this a spiral sink. Okay, so that's when solutions are going to spiral in towards the origin. And if the real part alpha of the eigenvalue is positive, then the origin is unstable. And in that case, when they're complex, it's going to be a spiral source. Okay, so here's kind of the big summary of phase plane dynamics and what do the eigenvalues tell us about the stability of the equilibrium, which in this case is the origin. What do they tell us about the stability of the equilibrium of the system?